Well, good morning, everybody. My name is Ashutosh Garg. I work at Furnace Improvements. Furnace Improvements completed 25 years of training of business in US and India. So we thought of doing training and interacting with you. So we want to talk to you, interact with you, and see what you feel. So we have this 90 minutes training. I'm planning to have about 4 sessions of 90 minutes each, and we we will cover most of the things. In addition, I want to thank you. We have received almost 120 questions from you. They are all very good questions. So we will try to answer those questions and post them on our LinkedIn page and Facebook page, and that will we will be able to answer all your queries and continue our dialogue. So you can always send me more questions and we will try to answer so many of these questions. Fire heaters, as all of you know, is a very unique equipment. It is the only equipment which can be easily overfired. It has been in the news for last 50 years for several reasons. It is a major energy consumer. So fired heaters they consume energy. Second, when they consume energy, they are also major polluters. So right now, as all of you must have heard about greenhouse gas emissions. Prior to that, for the last 30 years, we had been talking about NOx emissions. So fired heaters have been in attention for last as long as 50 years now. Other thing about fired heaters is it is the only equipment in the refinery which has open flames. So with that being said, it is the only equipment, and when you open the PEEP door, you are exposed to the flames. Also, you can increase the capacity of fired heater just by opening the fuel gas valve. This is the only equipment where you can continue to increase the firing rate and keep on getting more heat duty. So that is another feature of fired heater. And it also has, because of this, it also has a number of problems. So what we want to do is we want to start and my first question is a poll question for you. What are the typical problems in fired heaters? So on your phone, you can select one which kind of you think it's the most important problem or the most pressing problem or what you have experienced in your time. You can write it down, you can click it. I only had 4 selections available here. I think we have another slide for the 4 more problems. But what we want is, let's identify the problems. Let's hear from the end users. Let's find out what they think are the problems rather than my telling these are the problems. So please, on your phone, you can select one of the 4 answers. And that way we will know what are the pressing problems in fired heaters. It could be positive pressure at arch. You could be worried about high flue gas temperature in stack. I can tell you so many of my colleagues in India, because of the high fuel gas cost or high energy cost are really worried about flue gas temperature leaving the stack, and they want to cool it down almost to ambient if it's possible. So we will discuss that as well. So we have 34 answers. We will just see how people rate. So 8 people think positive pressure at arch is the problem. 13 people, 13 votes for high flue gas temperature in stack. 19 people high tube metal temperatures, and some people 8 are kind of thinking heater pass outlet temperature variation. So thank you for your vote. We will move to the next. So you can see these are the problems which are very common. I added some more problems in fired heaters and things like flame impingement, charge limiting, short run length, bowing of tubes. So just think about what could be happening in your fired heaters and what are the issues which you are facing. So we could identify and then have more attention on these topics. As you all know, for furnace improvement specializes in fixing of fired heaters. That's what we do for living. We are always improving the performance of fired heaters, whether we are fixing the short run length issue or flame impingement. All right. So 67% think flame impingement is a big problem, and I agree very much with them because we also feel flame impingement has been exacerbated ever since we got the low NOx burners. Ever since we got the low NOx burners with double or triple the flame length, flame impingement problem has been experienced in number of heaters. And then the short run length, that's another, I think maybe a direct relation coming from flame impingement. So thank you again. Good response. So where do we use fired heaters? You know, given a choice, I think process engineers won't like to even put a fired heater. I mean, they may want to use a heat exchanger, or something similar. So uh, let's find out where are the fired heaters being used. So most of the 50% application is in preheating charge to a distillation column, maybe like a crude column or vacuum column. Some places it could be preheating charge to a reactor like a hydrotreater or hydrocracker. Some could be sensible heating of fluid, which is like maybe a hot oil heater. And then the other application, which is producing ethylene or hydrogen. So I'm happy there are 3 people who kind of have ethylene applications. So if you have a fired heater, why don't you let me know what is the outlet temperature of the fluid in your fired heater? To what temperature do you heat the fired heater? It appears to me that I have only given 30 seconds, so you need to act quick. Maybe next time I can add more time, but uh, since we have limited time, I kind of this thing. So most of the heaters, as you can see, heat the fluid to about 600 to 800 degrees F. That's typically. There are some heaters, maybe like coker heaters or maybe platformer heaters, where we go up to 1000 degrees. Less than 600 are typically hot oil heaters or maybe reboilers. And then 14 to 1600 range is in the steam methane reformers or ethylene crackers. Those are specialized testing. So you can see that we have applications of fired heaters with different outlet temperatures. So my question here is, can you achieve 900 degrees outlet fluid temperature using steam or hot oil? Is it true or it is false? Well, nobody thinks we can get up to, most of the people think we cannot get up to 900 degrees outlet fluid temperature using steam or hot oil. And I think it's very important to understand that process engineers use heat exchangers as their first choice. And in the heat exchangers, you can have steam heating, you can have hot oil heating. But after 600 or 700 degrees temperature, uh, the hot oil start coking up and the steam pressure keeps on going up. To achieve 900 degrees, the fluid has to be at least at about 1000 degrees so that we can have the approach. So that is one reason we find that uh, the heat exchangers cannot be used in place of fired heaters. This reminds me of a story, and it was there was a Russian engineer who designed a nuclear-powered refinery. He said, we will just put one nuclear reactor in the center of the refinery, and I will supply the heat to all the users from that reactor. But he ran into problems, and the problem was he could not find a suitable fluid who could heat or transfer heat at 900 degrees or even 1000 degrees. So he ran into problems. I mean, even molten salt cannot do it. So that's one reason why fired heaters cannot be replaced with heat exchangers. So just to give you an picture on refining industry in the US, we are in the survival mode. The number of refineries have been coming down. 40 years ago, I think there were more than 300 refineries in this country. Today, we have only 120 refineries operating. The good news is the refining capacity in the US has more or less remained steady or even has gone up. That means the existing refineries are being revamped every 5, 7, 10 years to increase the capacity. So my guess is approximately there are about 2,200 heaters in the US, out of which 90% of the heaters are natural draft. 8% of the heaters are with forced draft and only 3% heaters are with the air preheater. This picture is very different when you go to Asia. In Asia, you will find, because of the high fuel gas cost, 90% of the heaters are balanced draft, or 85% of the heaters are balanced draft with air preheating system because the fuel gas cost is very, very high. Average size of heater in the industry is about 72 million BTUs. The forced draft or the balanced draft heaters tends to be bigger at about 110 million BTUs. So that is a picture. So fired heaters is nothing but a large heat exchanger. They are used for high temperature heat transfer. The energy for heat transfer comes from the combustion of fuel, and radiation heat transfer plays a very significant role. And we will talk about many variations of fired heaters: single fired, double fired, top supported, bottom supported, vertical and horizontal tubes. So we will talk all about that. So here is a guess. You want to take a guess. What is the temperature of the flames? I'm looking for the adiabatic temperature where before giving out the heat. So some people think, okay, most people think the flame temperatures is in the range of 1500 to 2000 or 2000 to 2500 or 2500 to 3000. The real temperature of the flame before it gives out the heat is in the range of 3000 to 4000 degrees F or 1650 to 2200 degrees C. So you can see the flames are really, really hot. If you look at methane, ethane, we will go more into that. They typically tend to burn around 3200 degrees. If you talk about carbon monoxide, you talk about hydrogen, you talk about ethylene, propylene, acetylene, you will see their range in 4000 degrees F range. So these are the adiabatic flame temperature we are talking about. So flames are really, really hot, and that is why we are able to heat up to 1500 or 1600 degree F in ethylene crackers or 1400 to 1500 degrees F in steam reformers. So flames play an important role in heat transfer radiation, So what is the typical temperature in the radiant section or a firebox? I'm talking more about the refinery heaters. What type of temperature can we expect in the refinery heaters and this is after giving the heat, after the flames have given out the heat. What is the temperature? So the correct answer is around 750 to 950 degrees centigrade, and most of you got it right, or 1400 to 1800 degrees F. That's the right temperature. Below this temperature, the radiant heat transfer is not very effective. And we will talk more about it, but anything less than below 1400, the Stephen-Boltzmann equation or the radiant heat transfer is not very effective. So that's where I think we kind of keep it around 1400 to 1800 to get our heat transfer. So what is the flue gas temperature leaving your stack? I think maybe we need more time for our participants. That's what it appears to me. Or maybe they have some slow internet connection. So I think the lowest temperature we have is 150 degrees centigrade at 300 degrees F. I think most of people in India must have been targeting 300 degrees. Then there are some people with even 500 degrees stack temperature. There are some with even 1000 degrees stack temperature. So 1000 degrees stack temperature, I would say, is very, very high, or even 700 is high. And we can go for improvement. But as you can see, most of the temperatures is in the range of 300 to 500 degrees, 80%, or 150 to 250 degrees centigrade. So as I said, typical temperature of flame for hydrocarbons is about 3000 to 3200. Temperature of flue gas leaving the radiant section 14 to 1600. Temperature of flue gas leaving the convection 600 to 800 degrees, and then temperature of flue gas leaving air preheater is around 300 to 400 degrees F, or 150 to 250 degrees centigrade. Now we want to talk about what type of fluid heating is occurring in your fired heater. Is it the sensible heating? Is it the latent heat? Is it the sensible heat and latent heat? Or is it the sensible heat, latent heat, and reaction? So we can have a different types of heatings taking place in fired heaters. If you have a hot oil heater, it is mostly sensible heating. If you have a reboiler, it is mostly latent heating. Sensible heating and latent heating is in most of the heaters, crude heaters, vacuum heaters, where we have both sensible and latent heat. And then we have reaction furnaces where we have all types, sensible heating, latent heating, and reaction also taking place. So you can see we can use fired heater for many applications. As you can see, we have some people with reaction furnaces, some people with sensible heating, but most of the furnaces have sensible heating and latent heating. So that's typically. So simple heating without phase change could be all liquid heating like a hot oil heating, or all vapor heating could be like a catalytic reformer or platformer heating where we have the vapor coming in, vapor going out, or we have the heating with phase change, means liquid coming in, but liquid plus vapor going out. So in that category, we have fractionator feed, reboilers, crude charge heaters. So that's typically are the type of applications. And these are the different reboilers that are used in the industry: column reboilers, reactor feed heaters, hot oil heaters, different heaters in the industry, hydrocracker, hydrotreaters. So all these heaters are used in the industry. So let's talk about what is heat. We have been talking about heat transfer, fired heater. So let us understand what is heat. So I think almost everybody got it right. Heat is a form of energy. So energy can neither be created nor destroyed, but it can be transferred. Let's talk about units of heat. What are the units of heat, what we measure? The reason I'm talking about units of heat is because a lot of operating engineers uh, think about the charge rate. Hey, am I able to push 10,000 barrels or 15,000 barrels? But the heater is supposed to transfer the heat. So they need to know what is the capacity of their fired heater. So all the answers are correct. I can see some people measuring in million kilocalories. Some people go with MKs, kilojoules. Most of the people in US measure it in million BTUs and then megawatts. So that's another thing. Thanks for your input. So this one is a little different actually. I'm asking you to type your answer. You can just type a number, What is the heat duty of your fired heater in million BTU or million kilocal? If you want to put units, it's fine. If you don't have space or this thing, but we need to know what is the size of your fired heater. The heaters can range anywhere between 1 million BTU to 1,000 million BTUs. I mean, that the largest heater which we have worked on has been around 1,000 million BTUs or 250 million kilocalories. So the heaters, of course, we have worked on small heaters also, but so some of my friends have really large heaters. So thank you for your input. So heat is a form of energy. Heat can be transferred from one place to another. We already talked about heat units. We already talked about what is the capacity of your fired heaters. And we will talk about later about firing duty, firing rate, and process duty. That's also very important because that kind of goes into efficiency. So we'll talk about that. And if you are an owner operator, the objective is lowest operating cost, minimum downtime, and proper operation. So that's typically what we want to achieve in our fired heaters. We want maximum efficiency, minimum emissions. Also, that's another minimum greenhouse gases, high run lengths. We want our heater to run forever, maybe 6 years to even 8 years, no repairs, and most importantly, safe operation. We don't want to have any accident. We want everybody to be safe day in, day out. But we want to talk about different types of heaters, components of heaters, and how the heaters started actually. I mean, as all of you know, the refining industry is about maybe little more than 120 years old. That's what. And when we started, when we started the refining industry, the heaters used to be in altogether different shape. We used to have shell type heaters or tank type heaters, and they were a batch process. So they would have multiple heaters, and as they would coke up, they will shut it down, clean it up, and then move on. Then they started looking at and invented this thing called pipe still. So there they kind of had fluid heating in pipe, but all those heaters used to have tubes located in the convection section. So there was no radiant heat transfer taking place. And there also we would have a lot of coking taking place in these heaters, pipe stills. So by example, by trial and error, they kind of worked out and saw, hey, okay, maybe we need to start placing tubes in the radiant section. So initially, it was all convective heating. So you can think about your fired heater like what you have, with no tubes in the radiant and all the tubes in the convection section. So that is how the next round of, after shell stills, we got pipe stills. So that is how the second one kind of started. And then we realized that, hey, okay, we need to start putting tubes in the radiant section. And that is how somewhere around, I would say 1930s, people started moving towards radiant section. And in 1940s, there were two engineers, very famous engineers, Lobo and Evans. They wrote a paper about designing fired heaters using radiant tubes. And all I can tell you is, till today, everybody uses the same correlation, whether it is vendor A, vendor B, Foster Wheeler, Lummus, anybody, they all use the same correlation of Lobo and Evans for designing fired heaters. All right, looks like everybody has logged in, so let us start. So where is the major heat transfer taking place in a fired heater? Okay, almost 3/4 of people got it right. Radiant section is the place where most of the heat transfer is taking place in a fired heater. Almost 60 to 80% of the heat in present day fired heaters is absorbed or transferred in the radiant sections. Convection section is important, but it does only 20 to 40% at the most. That is typically the ratio, where the heat is transferred. Where does the fluid which is heating in the furnace first enters? Is it enters the shock bank, the radiant section, convection section, or burners? So most of you got it right. The fluid enters the heater in the convection section, and the reason for that is that fluid is the coldest when it is entering the heater. So we can have the most efficient heat transfer in the convection section by lowering the flue gas within 50 °F of the inlet temperature. So we can have, for efficiency reasons, to maximize the efficiency of the fired heater, we have the fluid entering the furnace in the convection section and then going to the radiant section. What is the main function of the stack? All right, I think everybody, almost most of the people got it right. The function of the stack is safe disposal of flue gases, safe disposal of hazardous pollutants like NOx, CO, sulfur dioxide, sulfur trioxide. So and then creating draft in the radiant section. As most of you know that fired heaters work on negative pressure. They are inherently safe equipment. So stacks perform that function also by creating negative pressure in the radiant section. So all of the above is the correct answer. Thank you all. So three main components in fired heaters are radiant section, convection section, and stack. There are some heaters where we don't have convection section and we just have the radiant section and stack, and they are mostly used for startup services, all in small heaters. Radiant section, as I said, is the most important, and we can again divide the radiant section in three components. We can divide it into firebox, which is the steel casing, refractory, and tube supports. And then we have the radiant coil consisting of tubes and vents where the heat transfer is taking place. And then burners. Burners are on the floor or anywhere other places, but burners are the ones which are providing the heat, or burners are basically providing the flame for heat transfer. So that's basically three major components in the radiant section. This is a plan view of a vertical cylindrical heater. You can see over here, we have the outside casing, structural supports over here, and then we have the refractory lining on the outside and tubes in a circle, and then we have burners in a circle, and then there is an access door. We have peep doors. So that's typically how the heater floor for a vertical cylindrical heater will look like. This is a cabin heater, horizontal tube cabin heater, and here we are showing you the upper radiant section and arch section. Arch is basically the roof of the radiant section, and then we have the convection section, and you can see the header boxes of the convection and the radiant over here. That's basically how the upper section and radiant section are. And then we are talking of the convection section. So convection section in fired heaters generally has the same shape. We have tubes in a horizontal manner arranged in a triangular pitch at 2D spacing most of the time. The first three rows are bare tubes, and then we have finned or studded tubes for better heat transfer. So that's typically how the convection section is designed. So this is a plan view of a convection section on a vertical cylindrical heater. This is the fluid inlets you can see over here, and then the pipe which transfers the fluid from the convection section to the radiant section is known as crossovers. And these days we always have external crossovers for ease of construction. We also have a tube pulling door for removing tubes in the radiant section. This is the cross-section view of the convection section here. So convection section can consist of bare tubes in the bottom, you can see over here. And then we have fin tubes and studded tubes over here. And we have refractory baffles on both sides to prevent flue gas bypassing. That's typically how the convection sections are constructed. We are showing fin tubes and we are showing studded tubes. Fin tubes are used in gas firing. Studded tubes are used in oil firing. So that's basically how the difference. Most of the heaters these days, since we are firing gas only, have fin tubes. And then we have intermediate tube sheets because horizontal tubes require supports every 35 diameters. So we have these high alloy tube sheets which support the convection section tubes every 35 diameters. That's typically how the construction is. And then once the heat is recovered, we have the flue gas offtakes, you can see over here, and then you can see the stack, which is used for disposing the flue gas. We also have a damper here. So that's typically how this is the convection section, this is the radiant section, So that's the third component, basically the stack and the offtakes. So as we said, stacks have an important function of creating draft. And you can see over here in this picture, ladders, platforms, helical strakes for keeping the stack structurally stable. That's typically what we have. And then we sometimes have stack tip with a reduced diameter for higher flue gas velocity. So that's basically how the stacks are functioning. So let's talk about different types of heaters. The heaters can be classified in a number of ways. We can classify it as per firebox, as per the coil layout, how the firing is, and how the draft is provided. So they basically dependent on different types. So we have two configurations, vertical cylindrical and box heaters. These are the two configurations what we normally have. So I want to find out what is the orientation of your radiant coil. Radiant coil. So is it vertical, is it horizontal, is it helical, or none of these? So most of the heaters or majority of you have answered vertical coils, 60%, and 30% have answered horizontal. Helical coils are used in small heaters. Horizontal coils were historically provided in all the old heaters. All the old heaters used to have horizontal coils. And slowly the industry has been moving towards vertical coils because vertical coils are easier to support. You can support it from the top, and then basically you don't need to have any intermediate support. So vertical tubes are remain straight also. So because of that, vertical tubes are preferred nowadays. As you can see over here, 61% of people are saying. So this is the horizontal tube heater, cabin heater, and this is a vertical tube heater. You can see over here, vertical tube heater. Vertical cylindrical heaters are generally having vertical tubes. So I want to ask you, how are your radiant tubes supported? Are they supported from horizontal supports if they have horizontal? If you have vertical, are they supported from top or they are supported from bottom? Or maybe you don't have any supports. Doesn't look like that to be the case, but that could be another option here. So as you can see, top in vertical heaters, top support is most common. Bottom support is used in smaller heaters, and horizontal supports are used in horizontal tube heaters. So of course, nobody has no supports, everybody has some type of supports. And along with supports, we have guides. So typically, if it's a top supported, we will have bottom guided. If we have bottom supported, it will be top guided. And even sometimes intermediate guides are also there. On horizontal supports, we don't need any guides, but we do need some locking bars for preventing the jumping of tubes. That is provided in reboiler services or vaporizing services. That's typically how. So this is a picture of a radiant tube guide. As I said, it's important to have these guides free because these tubes are supposed to expand downwards when they get heated up. So these things needs to be free. Otherwise, what will happen is if they are stuck, you may get bowing of tubes. So sometimes bowing of tubes is because both ends are restricted, so the tube has nowhere to go but to bow. Two common configurations. Vertical cylindrical heater is a very common configuration, and horizontal tube cabin heater is another common configuration. So most of the heaters today are built in these two configurations, although if you look at 50 years old or 100-year-old heater, 70 years old heater, you will see all sorts of shapes and sizes which were built by the refiners at that time. So here is a question for you. Where are your burners located? Are they on the roof, floor, sidewall, end walls? So typically burners are on the roof in steam methane reformers. Well, as you can see, most of the heaters have floor firing, and that is the most common these days. In the old days, old heaters, we would have burners on the end firing horizontally, or some heaters like steam methane reformers or even cracking heaters. Ethylene cracking heaters have burners on the side walls. Roof is only steam methane reformers firing down. So, well, thank you for your feedback. One of the things which is very important is uniform heat distribution, and the burner's location and the number is one of the main causes how these get how important or how the heat distribution is created. So burner layout, we could have, as I said, floor firing, end wall firing, side wall firing. There is another firing which is terrace wall firing, was promoted by Foster Wheeler for steam methane reformers. So it's also very good way of firing. This is the end wall firing you can see over here. That is how all the old heaters used to be designed, end wall firing. Now we move to vertical firing or vertically up, and I think that is much, much better because of the buoyancy. The flue gases have a tendency to rise, so we can have straight flames. Then this is almost like a terrace wall firing you can see over here, or bi-level firing. There are several cracking furnaces where we have this type of firing. And then this is again a very old design where the burners are firing against a bridge wall in the center. And then we have the radiant tubes on the top. So that's kind of a sidewall firing, but that's typically the different. So another way we can classify the heaters is by draft. Whether you have a natural draft heater, whether you have a forced draft heater, induced draft or balanced draft. So two drafts are very common, natural draft and balanced draft in the refining industry. That's typically the most common configurations of heaters. So again, we want to find out from you what type of draft system do you have on your fired heater, whether it is an induced draft, forced draft. Forced draft firing means you have an FD fan only. Induced draft firing means you have an ID fan only. Balanced draft firing means you have both the fans, both FD and ID, and most probably you will have an air preheater. And the natural draft firing means no fans. So that's typically how you can configure. So most of the furnaces or majority answered natural draft. Some people have balanced draft. Some people have forced draft, which is unusual, but hey, anything is possible. I really like forced draft furnaces because they have shorter flames. And then we have induced draft furnaces. So thank you for your feedback. Natural draft heaters, the stack creates a draft, no fans are required, and most common configuration in the refineries in the USA. They are the least expensive, most reliable, but also least efficient. So I think that is another area for when we are talking of greenhouse gas emissions that gives us a lot of potential to improve the efficiency of these natural draft furnaces, at least by about 10%, if not more, to reduce the emissions, greenhouse gas emissions. Balanced draft, as I said, is the one where we have the air preheater. We have a FD fan and the supplying the cold air to the air preheater, and it's preheated in the air preheater, and then hot air goes to the burners, and hot flue gas goes to the air preheater. Heat is recovered, and through an ID fan, the flue gases are sent back to stack. So this is a very common configuration in the refinery, especially in India and in Asia, where the Fuel gas prices are very, very high. These furnaces are about 90–95% efficient. So very this thing. So I think this is what type of heater do you have? Do you have a horizontal tube cabin heater? You have a vertical cylindrical heater? You have a twin cell heater, or you have any other type of heater? So most of the people either have vertical cylindrical heater or horizontal tube cabin heaters, and some have twin cell heaters. So it's all split up. So now I want to talk about some of the common types of heaters. A vertical cylindrical heater with horizontal convection section, very, very popular. It is considered the workhorse in the industry, has a lot of advantages. Uh, Vertical cylindrical heaters became popular in 1950s. Low plot space, economical. We can have any number of passes. The convection section is very compact. Tubes can go up to, vertical tubes can go up to 60–65 feet. And heaters are built into this configuration. We can have heaters up to 150 or 200 by combining having two radiant cells. But generally 70 up to 75, this is a pretty good number for that. Horizontal tube cabin heaters, again, very, very popular. As I said, old heaters all used to be horizontal tubes. We can have it with a sloping arch, or we can have it with a flat arch. So those are the two variations. When we have a flat arch, we call it a box heater. When we have a sloping arch, we call it a cabin heater. So not much difference there. And then this is another configuration. We have a double fired vertical tube box heater, and the size is 20 to 200 million BTU. This is a configuration which is used in steam methane reformers, is used in cracking furnaces, also used in hydrotreater and hydrocracker heaters. So here the tubes are in the center and we are firing from both the sides. That's typically what we do. So that's typically the configuration. Again, very, very popular configuration. And then we have heaters for CCR, or what we call it a platformer. That's another configuration where we have large volume of gas to be heated. So we have large manifolds on the top or on the bottom. And then we have the U coils or inverted U, which we call it like an arbor. So and the burners can be on the walls. Burners can also be on the floor. And these can be double fired or these could be single fired. So these are the many configurations available for these heaters. That's again a common type of configuration. We will be talking about combustion. Combustion is one unit operation which happens only in heaters and boilers, does not happen in any other equipment in the refinery. So that is what differentiates fired heaters from heat exchangers or any other equipment, So very, very different type of unit operation, and combustion, in my opinion, is one of the most important operation which is taking place in fired heaters. Combustion is always working actually. So we are also tight on time, so we'll start and try to complete this. So we'll talk about combustion and efficiency today in the last session of this webinar. So we have a combustion reaction is happens in liquid phase, happens in solid phase, or happens in gas phase. Well, most of you got it right. Combustion reaction happens in gas phase. So even if you are burning liquid fuels or even if you are burning solid fuels, the combustion reaction happens in gas phase. Both the reactants needs to be in the gas phase for the combustion to occur. Thank you. So combustion requires following: oxygen, combustible fuel, a source of heat energy, or all of the above. Most of you got right. We need a combustible fuel, we need a source of oxygen, and we need a source of heat to start the combustion. So all of the above is the correct answer. Without this, it will not work. Okay, so this was supposed to be in the end, but maybe it has got, I don't know, it became like a random. So anyway, best time for holding a webinar, I wanted to ask you whether we should do it at 7 a.m., 8 a.m., 9 a.m., or 10 a.m. CST. What is the best time? So well, 68% are saying 10 a.m. So I will continue doing my training at 10 a.m. CST. Thank you. Right before lunch. Combustion reaction is a photochemical reaction, an endothermic reaction, an autocatalytic reaction, or an exothermic reaction. Well, most of you got it right. Combustion is an exothermic reaction liberating heat, and that is why we are using combustion in fired heaters, where we are converting the chemical energy in the fuel to thermal energy. So whatever is stored in the fuel as chemical energy, that is released in form of thermal energy via combustion. The combustion process is usually accompanied by well, most of you got it right. Rise in temperature and pressure. I mean, the temperature is rising, and because of the temperature, the pressure also goes up. Thank you. Let's go to the next question. Now, we are all familiar with excess O2 or excess air for completing the combustion. Why do we supply the excess air? Is it for obstruction of inert gas molecules, chemical equilibrium, incomplete mixing of fuel and air, or all of the above? Incomplete mixing of fuel and air is the correct answer. That is why we supply excess air so that all the fuel can burn in the given amount of time. So the other choice would be providing excess fuel and consuming all the air, but that will not be a good efficient choice. Okay, that's an easy one. Combustion is a chemical reaction between fuel and oxygen producing heat. Thank you. Everybody got it right. So you are all combustion engineers. What is stored in fuel? Is it mechanical energy, chemical energy, electrical energy, or thermal energy? So I think we already discussed it. It is the chemical energy which is stored in the fuel, and by process of combustion, we are transferring the chemical energy into thermal energy. So that's what are the three main ingredients for combustion? What do we need for combustion? Thank you. Everybody got it right. Fuel, oxygen, and heat. These are the three things we need to start the combustion. So, but once we have the heat, then the combustion is self-sustaining, and so chemical energy is stored in fuel. This energy is released in the form of thermal energy by fuel, and combustion is central to conversion of chemical energy into thermal energy. And the chemical reaction is taking place between fuel and oxygen. Oxygen, we normally get it from air, and the products of combustion are called flue gases. So fuel and air combust to produce flue gases, and that's the combustion. So combustion has several properties, you can say. First of all, it is a spontaneous reaction. It happens very, very fast. Also, it's an irreversible exothermic reaction, because once it starts, you cannot take it back. It has to be uh, keep on going. The reaction time is normally in milliseconds. Especially for the gas components, it's in the milliseconds. It happens very fast. And fuel has three major components: carbon, hydrogen, and sulfur. The first two are desirable components, and the third one is undesirable component. It happens only in small amounts, but it still causes us a lot of pain. And oxygen, we are lucky to get free oxygen from air. So we are not paying for the oxygen. What type of reaction is, I think we already had it, but anyway. Almost everybody got it right. Exothermic. What are the 3 T's needed for good combustion? I think it should be pretty clear. I mean, the only option with 3 T's is time, temperature, and turbulence. We need to have good mixing, we need to have right temperature, and then we need to have good timing for mixing. Thank you. So the 3 T's of combustion, as we call it, is fuel and air mixture needs time to combust. Temperature, that mixture needs to be above the minimum ignition temperature. And turbulence, we need to mix very well. Every fuel gas molecule needs to find the oxygen molecule to have good combustion. So mixing is very, very important in combustion. So here we are talking about minimum ignition temperature. As we said, we need a minimum ignition temperature for any fuel to burn. And that is why we need a source of heat. Now, in most of the burners, we have pilot burner or an ignition torch acting as a source of heat. That's how we supply it. So we need that. Now, another thing which we need to talk about is the flammability limits, because if you just have fuel and air, it is not necessary that they will burn. They need to be in the right proportion. And that proportion is known as between the lower limit is known as LEL and the upper limit is known as UEL, upper explosive limit. So as long as the fuel composition or fuel percentage is between the LEL and UEL, you will have the combustion. If it's below LEL, it will not combust. If it's above UEL, it will not combust. And those of you who are in the operating plants will see how it works out with an explosive meter. So these are the flammability limits for air. The only thing I want to point out in this table is number 1, hydrogen. We are all talking of burning hydrogen, but you see hydrogen has the widest range of flammability from 4 to 74%. All the other gases are 5 to 15, 2 to 36, very narrow range for burning. So those are much safer to handle. Hydrogen has a flammability limit from 4 to 74, so it does require special handling. This should be an easy one. How much oxygen percentage by volume is in air? If most of you got it right, 21%. So combustion air is 21% oxygen and 79% nitrogen. Now, nitrogen does not take part in chemical reaction. It is like an inert. It enters the heater at 60 degrees and leaves the stack at 300, 400, 500 and contributing to the heat loss. So our option is minimizing combustion air so that we can reduce the nitrogen volume. That's how we get our efficiency in the heater. Already talked about, the fuels have 2 types of heating values. Higher heating value is called HHV, and that is the heat released when we from the combustion of a fuel. When the combustion starts, combustion is complete, and we condense the water vapor into liquid. So that is the higher heating value, and lower heating value is when we have the water vapor in the vapor phase and it's not included. So basically that's the difference between higher heating value and the lower heating value. So this is a little trick question. I don't know if you know, but what is the lower heating value of methane? If you can guess, that will be really good. Methane is a very clean fuel. It is my favorite fuel. 95% of natural gas is pure methane. Methane also burns the coolest. So I really like it. Well, the correct answer is 900 BTU per cubic feet. I think some of you put 1,000, some of you put 1,100, which was very close. So that's the heating value of methane. This is a chart of heating value. We have the molecular weight of paraffins, hydrocarbons over here, and then we have the heating value on the y-axis. You can see over here the heating value is almost like a proportional straight line actually. The lower one is a lower heating value. The red color is a higher heating value or gross heating value. So that's another thing we want to talk about is the flame temperature. Flame temperature, the adiabatic flame temperature is the temperature which the products of combustion achieve without any heat loss. And you can calculate it by the heat release divided by the weight of combustion products and specific heat. Now, the actual flame temperatures are much lower because they immediately lose heat to the surroundings. So that's one reason why nobody is able to measure the actual flame temperatures. So these are the theoretical flame temperatures, and you can see over here which gas burns the hottest. We have not listed carbon monoxide and acetylene, but they are one of the gases which are burning very hot. But as you can see, most of the flame temperatures are in the range of 3,500 to 4,000 degrees F. That's how hot the flames are. Another thing you want to minimize for efficient combustion is the oxygen content in the flue gas. And this curve shows you the relationship between the oxygen content and the excess air. So if you have 4% oxygen in the flue gas, you are looking at 20% excess air. If you have 6%, then you are looking at 40%. So basically that chart is available at so many places, but it gives you an idea that you need to keep on reducing the excess O2 to get more and more efficient. What is flame? So flame is a visible part of combustion reaction, and we have a mixture velocity of the fuel gas and air which is coming out of the burner tip. At the same time, we have the flame velocity, and when both match, we have the flames coming out. So that's basically the shape of the flames. If you have a high velocity, the flames may lift up from the tip, or if you have a low velocity, the flames may start flashing back. So some people talk about color of flames. I don't think that's very important. It basically is depending on how the combustion process is taking place. So here is a poll question for you. What is the thermal efficiency of your fired heater? Uh, Well, most of the fired heaters have efficiency between 75 to 85%, and some have even 85 to 90%, and there are maybe cracking furnaces which are in the 90 to 95% range, so pretty good number. So you can see in 1960s, the thermal efficiency was pretty low of the heater, somewhere around 75% was considered good. And then as the oil prices started going up, energy price started going up, and we had the oil price, first oil crisis and then the second oil crisis. So now we have kind of stabilized at about 94% efficiency. That's typically where we kind of call it, it may go to even higher, but I think that's typically what we are kind of guessing. So why do we don't have 100% efficient heater? And the reason is we have to have heat loss through the flue gases, and every 35-degree reduction in flue gas temperature increases the efficiency by 1%. And similarly, every 15% reduction in excess air improves the efficiency by 1%. So the stack temperature target, we can go around 200 to 250. This should be 20 degrees centigrade. I think this is wrong, actually, 1.67. We need to fix it. So how low can we go on stack flue gas temperature? All right, we have majority around 300 degrees. Some people can have gone up to 250. Some people want to go to 200 degrees. Let's see if we can successful, or 350. So we have a wide range now. And this is where the sulfur comes into action. If we don't have any sulfur in the fuel, then the water vapor in the flue gas that will condense depending on the vapor pressure of the water, which could be anywhere 125 to 130. So we can cool up to 130 without this. But what happens is sulfur burns and forms sulfur dioxide, and some part of it gets converted into sulfur trioxide, which reacts with water to make sulfuric acid. And the presence of sulfuric acid raises the acid dew point substantially, almost by 120 degrees or 150 degrees. So once that happens, the sulfuric acid starts condensing and we have corrosion problems. And here you can see the chart of weight percent H2S in the fuel gas, and you can see the dew point is anywhere starting from 240 to 360. So dew point is very, very important. You don't want to get into dew point, and that becomes like a limitation on efficiency. So fortunately, now we are burning clean fuel gases. There is a lot of effort on reducing the sulfur content in the fuel gases. So we can go down as low as possible, and maximize the efficiency. The next is waste heat recovery is very common in cracking and steam methane reformers. So air preheating or steam waste heat recovery are the two ways of maximizing the efficiency. So that kind of completes my training today. If you can provide me some feedback, that will be very, very helpful. Be very honest. This was the first time I used Kahoot, so hopefully I have learned quite a few things. Hopefully we will improve it. And so our plan is to continue this training, even covers cracking heaters and steam methane reformers we want to cover. And our plan is to do one session a month because it takes a lot of preparation to get these slides make, So hopefully, I hope you will continue joining us, and I will start putting the answers to your questions next time. So thank you all for the good feedback. So we had 140 people registered today. In fact, I had to decline 10 people because we said we have a capacity of only 100 people, but it looks like maybe either some people had technical difficulties or they were not able to join. I'll try to find it out. But we want to keep on communicating with you, and hopefully we will improve our presentation so that you can learn and we can also learn. Thank you. Thank you very much for your feedback. And then I think the last question is just, was this webinar useful? So once again, thank you all for giving me a patient hearing. Send me suggestions via email, chat. We want to modify this course and tailor for you. So thank you all for your time, and we'll see you next time. Thank you. Yeah, we can. This is there's. I think we tried to take out the points, but it still got it, so that's fine. All right. Well, that kind of completes our this thing. Let's see. So thank you all for joining, and have a nice day. Bye.